10.2 and 10.4, we're going to look at heat, the transfer of heat, and the controlling of heat. Okay, we're going to define it, we're going to relate it to thermal equilibrium, and we're going to talk about the modes of heat transfer. There are 3 modes of heat transfer that are studied by every mechanical engineer. Okay, any mechanical, thermal, fluid engineer have to know 3 modes of heat transfer. So first, to define heat. Heat is the energy transferred between the objects because of a temperature difference. Because of a temperature difference. So, for example, the radiator in the back of the room. The radiator, we'll talk about its mode of transfer, which is radiation. The radiator in the wintertime heats up, doesn't it? And if you stand near it, what do you feel? You feel heat. It's not a mystery. It's because that has a higher temperature than you and the air around you, so heat needs to flow somewhere. So heat is an imbalance of temperature, really. Okay, it's all it is. It's an imbalance of temperature somewhere, so heat wants to flow from one thing to another. Whether it flows by conduction, convection, or radiation is what we're interested in, really. Okay, that's what we're interested in. Now, diagram. So this is back to the can of soda, in this case juice. So you put a can of juice in ice water. The ice water temperature, is 5 degrees Celsius. It's a combination of ice and water, so it's a little bit above freezing zero. The temperature in the juice is 45 Celsius. Well, if the can is hotter than the actual ice water, the heat is going to flow out of the can. So what we want to write down is that heat always travels from hot to cold. Again, heat transfer is always from hot to cold. So in the summer, when you're cooling off, what are you really doing? You're giving off heat. But in the winter, when you're warming up, what are you doing? You're absorbing the heat. So it has to do with the relative temperature of 2 objects, thus bringing us back to the idea of equilibrium. After a long enough time period, this can of juice is sitting in this ice water bag. Well, eventually what happens? Look, they reach a state of equilibrium. The metallic atoms in the can walls vibrate, allowing heat to transfer via conduction and convection. I'll talk about those soon. Okay, so the molecules in the can vibrate, allowing heat to flow out of the can into the ice. When the heat flows out of the can of juice cools down. It cools off. It cools from 45 degrees Celsius all the way down to 11 degrees Celsius. Well, what happens to the ice water? It can't just sit there. It needs to absorb the heat. So it goes from 5 degrees Celsius up to 11 degrees Celsius. This is a basic principle of all thermodynamic cycles, of all air conditioners, fridges, radiators, anything. Okay, it involves the idea of heat transfer and flow. Now, which way is heat transferring when they're at equilibrium? The both arrows show, meaning there's no net heat transfer there. Okay, they're at equilibrium. At equilibrium. Look at some units of heat. First, we know that heat is really an addition or subtraction of energy. If I add energy to the system, I'm giving it heat, I'm increasing the temperature. If I remove energy, I'm decreasing it. So because we're looking at energy, we need to make sure that we're focused on our units here. Our units of energy we've looked at all year are joules. They are joules. Again, joules are a very small amount of energy. And we can see that in a moment. A calorie, not the calorie you're used to for foods. The calorie you're used to for foods is actually on the next line. That's called a kilocalorie or a dietary calorie. It's the same thing, these ones. But a calorie itself is the non-SI unit of heat that we used old times in chemistry and old physics. And it was around 4 joules of energy. But a kilocalorie, which is what we use in food, so if you go to eat food, right, you see on the label it has the amount of calories. Calories are what give you energy. You eat food so you have energy. If you don't burn off that energy, you gain weight because the energy stays with you. If you exercise and you play sports or you do some sort of motion, you're jogging, you're walking a lot, you're doing something, you burn that energy off, you burn off those calories. It's the whole concept of exercise. So calories that we know are these third and fourth rows here. With the capital C, that's the calorie we know of. And 1 1 calorie is equal to almost 4,186 joules of energy. So when you eat food, what you're doing is you're consuming energy, so you need to eventually burn off that energy. That doesn't mean that if you just don't eat food, you don't need to burn off that energy. If you don't eat food, you don't get nutrition, you become malnutrition then, right? So you eat food, hopefully good food, that you can burn off easily. It is a lot easier to burn off healthy food than it is to burn off fatty food. It is a lot easier. That's why people say, eat things like vegetables, eat things that are high in fiber, things that your body can, digest easily and burn off. When you eat things like sugar, you get energy, but sugar turns to fat eventually. Okay, I'm a prime example. I love sugar, but I eat a lot of sugar, and I definitely don't exercise enough. So eventually, you gain weight from things like sugar. And then obviously there's things like diabetes too. But just obviously for this idea here, understand the concept that a calorie is a large amount of joules of energy. Okay, so we have an idea of conversions here. The last one, which is actually really important because we see it a lot, is BTUs. Where do you see BTUs a lot? You may not have, but your parents definitely have. BTUs. Yeah, if you buy a refrigerator or an air conditioner or any heating unit, it's measured in BTUs, British thermal units. Okay, so what it'll say is it gives off this many BTUs, or is it concerned it consumes this many BTUs per hour. So it's really the amount of energy used by the actual appliance. You can take that amount of energy and you could actually use that a lot for conversions to power, or you can talk about the wattage as well. So let's talk about this before we get to the 3 modes of heat transfer. We're going to look at those 3 modes primarily tomorrow, but let's finish off with this concept here. When you do work, it's in quotes for a reason, because there's a phrase in engineering, to do work. When you do work on an object, what you're doing, when you do work, is you're changing the internal energy in that object. So for example, you stir something. What you're doing actually is you're actually heating it up. You're increasing the internal energy and you're increasing the kinetic energy there by doing work on an object. If you imagine, for example, there's a nail in the wall. I take the end of a hammer and I pry it into the nail and I pull it out of the wall. When that nail pulls out of the wall there, you're doing work to overcome friction. So what happens to it when you take it out, you feel it's a little bit hot. Next time you do that, you'll notice it right away. It's hot itself. Take a paper clip, bend it back and forth a lot. What are you doing? You're doing work. What do you notice? The temperature of that little joint where you're bending it. It increases. It will eventually snap in half because it becomes weak enough because you're affecting the molecular structure. But when you do work on an object, you're increasing the temperature. This also relates to the work kinetic energy theorem. You did work on the object, it increased the kinetic energy. Okay, but this is thermodynamic work that we're talking about here. Okay, you do work on a system. The 3 modes we're going to talk about tomorrow that we'll leave off with now are conduction, convection, and radiation. Okay, so let's pause at this point in time. We started talking about the 3 different modes of heat transfer. The 3 modes we listed were conduction, convection, and radiation. Now, specifically, we're going to start with conduction today. The whole concept of conduction is similar to that from electricity. When you charge by conduction with electricity, was the example where you rub your hair with a balloon, and because the 2 materials are in contact, they were able to transfer electrons. So conduction also involves either contact between 2 materials, or just the transfer of heat through one material. So imagine this rectangle as your desk in front of you. And for some reason you attach the heat source at this end of the conduction, or I guess at this end of the desk, right here. Okay, maybe we just separate it, which they are right here. The heat would spread throughout the desk in some sort of a fashion such as seen here. What is this called when you see these color schemes showing heat? What's the term for that? A gradient, okay? So the blue indicates colder, the hot is on the left, which is like this pinkish red. And the concept is that heat transfers from hot to cold. So look at the direction of conduction that it's occurring, to the right. You apply a heat source to one end, it eventually will spread, and it will continue to spread throughout that desk until it gets to the other end. Now, how does conduction work with more than one? With more than one. So you take 2 materials that are stuck together. Think about a computer chip and the heat sink that sits on top of it. In a computer, the CPU, the central processing unit, is what produces a lot of heat. Now, that would give off so much heat that it might overheat or the computer would not be able to run properly. So they take a metal block and place it right on top of that heat sink. The metal block absorbs a lot of the heat from the CPU. Now, we'll talk about how the metal block can get cooled off in a moment when we get to convection. Okay, but for now, the concept is if two materials are in contact, you have conduction. So when I was talking yesterday about touching this dry erase ledge, whatever this is called, it's made of metal. Metal can easily transmit thermal energy. Whereas if I take my hand and touch this piece of wood down here, it's the same temperature, but it does not easily transmit thermal energy. So the thermal energy transmitted to metal is easier to be transmitted than wood. What this is called, okay, this is called the K value of material. And not the spring constant this time, but this is actually the conductive coefficient. Conductive coefficient. Okay, conductive coefficient. So metals are traditionally good conductors of thermal energy. Gases. A gas is generally not a good conductor of thermal energy. It is not a good conductor. Now, let's take this idea and keep going with it before we get to convection. So imagine now, you look at a window. Okay, and if you look around the room at these windows are single pane, meaning it's a single piece of glass. Have you ever seen what a double pane window looks like? It's the concept behind a double pane window.
Isn't it like you have two panes of glass, and there's like a space in between them?
Yeah, that's exactly it. It's a piece of glass, there's an empty space in between, and then another piece of glass. Well, metals are good conductors of thermal energy, whereas gases are not. So what's the space in between probably? Some sort of insulation, good. Some gas or insulation. So the idea here, imagine you're in the room, so let's call this room over here. And we'll put outside over here. And in the middle will be our window. Here's a layer of glass. And in the between there's the gas region. I'll color it in red. And then here there's another layer of glass. Okay, the red is gas. Now, usually, the gas that's trapped in the windows that they fill it with is argon gas, which just happens to be a kind of gas that is not very volatile. It can't really hurt you. Has a low K value. It doesn't transmit heat easily at all. So you fill this pane here in between these glass pieces with this gas, and this gas acts as a barrier. It acts as an insulator. So although heat wants to leave the room in the wintertime and go out to the outside world, it has to go through not just a piece of glass now. It gets slowed down by this gas layer, and then there's another piece of glass after that. So this acts as insulation. That's what the red is showing you. It also works in the reverse. In the summertime when it's hot outside and it's cool inside. Right? It's nice and cool inside. You don't want the heat to come in. Like right now, it's cooler than it is outside. Outside, it is hotter than it is inside. So the heat wants to come in to the room because it's hotter outside. Remember, heat flows from hot to cold. So heat wants to flow into the room. But if you have double pane windows, heat insulates it even better also in the summer. It doesn't allow heat to flow in the summertime. So the concept of insulation works in both the winter and the summer. Okay, it works in both of those months. Or both of those times of years, whatever you'd like to say. But again, this acts as an insulation, the gas layer. Convection. So we're going to see convection has to do with the movement of the particles in a fluid. The movement of the particles in a fluid. So look at this first example. You have a tea kettle. You put it on the stove. You turn the flame on, it starts to heat up. What happens to the molecules? They get hot at the bottom. Hotter molecules are less dense, so they start to move to the top. So these warm molecules follow this red path. They flow toward the top. The molecules that were at the top, that were colder, what do? they sink down to the bottom. And you get this flow. So convection has to do with a fluid flow. Heating via or by convection has to do with fluid flow. Or cooling by convection. Have you ever taken a fan and waved it in front of your face? Why would a fan work? Why does that allow you to cool yourself off like this? Why do you do this when it's hot? What are you doing? What's the air around you called? What state of matter is the air around you? Gas. Gas is a fluid, isn't it? So when you're doing this, what are you doing? You're taking fluid and you're allowing the fluid to flow over the surface of your body. As a result, you're cooling the temperature. And what you'll notice if you study engineering, you go on to see this, the velocity of that fluid flow has a lot to do with how fast it cools off the surface. So if you take a fan and you change the level of the fan to the third or fourth level, it speeds up, doesn't it? Doesn't that cool you off much better than a fan that's not working that well? Because of convection. Okay, so the velocity has a big role in the convective nature or the heat transfer in convection. Now, anybody know how this would be used with computers? I alluded to in the last section. There's a part of a computer that involves fluid flow. What part of a computer? There's more than one answer that's possible here. Give me one of them.
Like a heat sink. Or okay, so no, but yeah. So the heat
Tell me how it works. I'll draw it. Go ahead.
So you have the piece of metal on the CPU, and then you have pipes that pipes that lead to a fan. And then you
Also known as fins. Okay, keep going.
and then I guess you have some fluid in the.
Oh, you're okay. You're doing the other one. Let me go back then. I'll go over that one in a minute. So you're doing something like this, where you have pipes that run over the surface of the heat sink. That's the other one's different though. That's why. So what Paul's talking about is there's pipes running over the surface of the heat sink. Okay.
And then it heats up, the pipes get heated up by the heat sink, and the fans, I guess, by convection, they cool off the pipes, and so it's removing heat from the CPU.
So the CPU is on the bottom of this metal block on the right here. It gives off heat. The heat gets absorbed by conduction by the heat sink. The heat sink has this fluid running around it that's really cold or it's chilling it, which cools down the heat sink itself. The fluid then heats up. When it exits in the pipe later on, a fan runs over the pipe to cool off that fluid. That fluid can also change pressure, which would make it recondense. This is like how a refrigerator really works. The other type of heat sink, anyone seen this one before? With fins? Yeah, it's like a radiator. Have you ever looked at you could look at these radiators, not a perfect example because these are pipes really, but each of these pipes are a fin. There's hot water flowing through the radiator. The surface area of these fins is what allows it to transmit heat via convection. So usually there's a fan blowing over something like this. The fan pushes hot air, it's called forced convection really. It pushes the hot air off of the surface of this hot radiator. The more surface area you have, the more convection or more heat transfer you can have. So on the left, that's what's happening here. This is a traditional heat sink on the left. Old school, thicker computers use this, where they had these metal sheets. And the metal sheets were called fins. Each of the sheets wanted to maximize area. So you might have 5 of these fins here, and there's heat coming from the heat sink into these fins. So these fins all get heated up. Each one of these gets heated up, but the fan in your computer blows forced convection or forced air through each of these channels. As a result, you feel on the side of your computer the hot air coming out. The fan is pushing across over the fins and removing the hot air from this material by pushing it away from you. So this is called forced convection. But convection in general occurs when there's a fluid flowing over a hot surface. Okay, those are 2 examples of that. How about radiative is something called the convective coefficient. Convective coefficient. And that's known as, well, I should just put an arrow instead, H. Okay, H is the convective coefficient. And H has to do with some properties such as the buoyancy of the fluid, the pressure differential, what else did I write down? And the conductive nature of the fluid itself. So H is a material property. You don't have to know much more about it besides the fact that if H is higher, more heat transfer occurs, just like the last one. As the K value increases, more heat transfer occurs via conduction in the last example. So for radiation, we seem to forget this a lot. Yet the Earth is given heat via radiation. It's not given heat the other ways. It's radiation. That's what's happening. Now, obviously the Earth heats up, right, when the sun hits it. It absorbs the energy. The Earth itself gives off energy. Ever in the summertime, you see like it looks like almost steam is coming from the ground, and it's really like heat waves. If you ever look at like asphalt, above blacktop asphalt, right? You'll see these like heat, like different, like it'll look like blurriness. What you're seeing there, okay, the Earth absorbs the heat, then fluid flows over it, but it's radiating the heat off, and it's convection at the same time. So radiation has to do with particles or waves traveling through medium of space. This is not involving a transfer of any matter. In the last one, you had matter flowing. There was gas. There was heat actually flowing through the through conductive nature. This itself has to do with EM waves being given off by an object. Okay? Now, humans give off EM waves also. If you look at humans in an infrared camera, you can see their heat signature. The color, you'll see like red in the middle, and then like orange and yellow, and then maybe like green. Eventually it may be blue outside of them. But the concept here is that you give off radiation if you have any temperature at all. So everything is giving off some sort of heat signature to itself, or from itself. So the three modes of heat transfer: conduction, which involves contact; convection, which involves fluid flow; radiation, which involves electromagnetic waves.
Would something at absolute zero have radiation?
No, because it would be absolute zero. That's the whole idea there. Okay, it would not give off any radiation there. Now, a lot of things involve not just one, but all three of these modes. Okay, not just one. For example, say you're in the fall and you go camping and you make a campfire and you want to heat something up. Well, the coals actually radiate heat. When the coals get hot enough, they radiate heat. When air flows into the fire, that's how combustion occurs. You need air flowing. That's why a fire, when you want to start a fire, you blow lightly into the kindling in the fire. As the heat is heating up, as it starts a fire, you want to blow very lightly. You need to add oxygen for combustion. That oxygen that continues to flow afterward, though, involves convection. And then conduction occurs if you were to heat something up. You put say you put a big pan on top of it, or a pot where you have water in it. You want to heat up that water. Well, conduction is occurring there because the heat from the flame hits the actual metal. Conduction is what heats the water, and then the water heats itself up via convection. So a lot of the time things are being heated. It's all three of these processes occurring at once. Okay? They're all related to one another.